Now, David, I'm just going to quickly introduce David. I'm going to stop sharing my screen. David's going to come on. David jumped in to answer in part because David's a co-founder of Passive Buildings Canada. And I was not around. So he was there in the early days along with Terrell and a few other folks. You've all been sent his bio, but we were all sitting around talking about who would be a great speaker and the importance of indoor air quality and COVID. And David's name kept coming up, and he very, very kindly agreed to come in and talk to us today. So we really appreciate it, David. And so welcome. And I'm going to stop sharing now.
So I'd like to talk to you this evening about identifying poorly ventilated spaces and how to rectify them with what I kind of call the triad of engineering controls, and that's ventilation, filtration, and ultraviolet light. And by the end of this presentation, you should be able to confidently recommend ways to improve indoor air quality for the COVID-19 pandemic as well as the future. So contents. First, I'd like to cover the basics of ventilation and how to improve a system. Next, I'll talk about how filters work and address a few myths about filtration that you might have heard of recently. Last, I'll look at ultraviolet germicidal irradiation and then put it all together as sort of a best practices package. So, but first, a story of how I got into this area. Like most people, back in March of 2020, I was wiping down surfaces and leaving groceries outside before bringing them in, and generally trying to avoid being sneezed or coughed on. And I was following Dr. Shelley Miller of University of Colorado Boulder on Twitter because of her indoor air quality work on from, say, gas ranges. So the issues with cooking with gas, essentially, and how that's been impacting health. And she started sharing information about airborne transmission of COVID-19. And at that point, I was starting to begin to wear a cloth mask. I felt too ashamed, actually, to wear an N95 in public because of the whole idea of needing to reserve them for healthcare workers. I had a stash of them left over from doing, you know, like industrial walkthroughs and just general like household carpentry or whatever. By the end of April 2020, ASHRAE, which is the engineering society I belong to, released its statement on COVID-19 in buildings, and they stated that airborne transmission was likely, and that heating, ventilation, and air conditioning systems can reduce it. During the summer, I started tweeting about ventilation, especially in schools, based on the energy audits that I'd been doing, and it kind of took off from there. So what is ventilation? We're pretty familiar with it within sort of the passive house idea, but it's the minimum amount of outdoor air required to control indoor contaminant levels. And the standard for that is ASHRAE 62.1 for non-residential buildings. And it's essentially based on minimal dissatisfaction, mostly with odor. It's not intended for disease control. It can be natural, which is, say, with open windows and other designs like that. It can be more traditionally or more usefully with mechanical systems. So a supply fan, an exhaust fan, or a combination of the two. And fundamentally, it's all about pressure differences. Air moves with pressure differences. We can create a positive pressure on one side and a negative pressure on the other with wind, and that can actually create enough airflow throughout a building to overcome mechanical pressures. Any fan or blower works by creating a pressure differential. And we're kind of familiar with the stack effect, which is different air temperatures creating pressure differences within a building. So you can have, you basically have, difference in pressure is related to airflow and vice versa, as long as you have a connecting path between the two sides of pressure. So how to assess ventilation? Quickly, You can look at the age and type of building. Before 1990 in Ontario, residential type buildings didn't need mechanical ventilation at all. So low-rise retirement homes built in the 80s didn't require bathroom exhaust fans if there was a window in the bathroom. And these still exist today. Most of them have been retrofitted, at least for bathroom exhaust fans, but many of them still just only have windows for ventilation. And these types of retirement homes and other congregate settings have had very high attack rates of COVID-19, even with everyone being vaccinated. Larger commercial buildings, including schools, had ventilation going back in time a little earlier, but it does vary with the year and with the local codes. So we can look back in sort of a historical of, say, in this example for classrooms, what the design ventilation rate, and it's changed over time. In the 1980s, it was, and specifically ASHRAE 62.1, was the ventilation rates were reduced in response to oil shocks. And that led, unfortunately, to sick building syndrome. So it was then increased in the 1990s, and then has been basically those levels ever since. And in the case of schools, it's works out to about 15 CFM per person. So when a school district says it's operating as designed, you can ask them which design year. Was it 1985? Because if it is, then we want to make sure that we investigate to make sure if it has been actually retrofitted since then to have the increased levels that are acceptable today. Pandemic guidance actually for schools is mostly from Harvard School of Public Health, and they're going back to a basically double, so 30 CFM per person, working out to an air change rate of 6 air changes per hour in a classroom. One of the ways that you can investigate ventilation effectiveness is to do a spot check with carbon dioxide. And you can do spot checks, you can do longer trending to see what it looks like over time. And one energy performance measure that's been used in commercial buildings for some time has been demand controlled ventilation, where the system is designed to only add more ventilation when CO2 exceeds a particular threshold, often around 1100 to 1200 parts per million. And now, though, you can get these nice little inexpensive, there we go, CO2 meters, very portable. The battery lasts for well over a year. It's got e-ink on it, which is why it doesn't, the display can keep going. It's really high right now because I'm breathing on it, but Bluetooth, and you can carry it everywhere. So I found that this is a fantastic thing I can bring with me wherever I go. So that particular unit's about $325 Canadian. Here's an example of what I used it for. Looked at, I put it in my daughter's backpack, and you see on December 8th, which is the red, the trend came back alarmingly high. And I had been sending it with her for a while to school, and in the fall it was fine. And I thought, I don't need to send it anymore, I'll just keep it at home. But I did send it on December 8th and noticed this alarming trend. And so I thought, okay, I'm gonna send it back the next day and see what happens. And it was back to sort of the normal levels the next day. So we can do some quick calculations as to what is expected, and that sort of number of 1200 parts per million that ASHRAE used to have in an older version of standard 62.1 for demand controlled ventilation. Yeah, it works out when you look at the activity rates of children in a classroom and how many there are. It kind of works out to, yeah, 1200 would be about the level that you would have for meeting code minimum level of ventilation. So most of the time it's been below that. It's been around 800 or a little bit above, a little bit below during the day. And that indicates that my daughter's classroom on ventilation alone was actually quite sufficient. So I asked the school about that, and it turns out they were rebalancing the heating system or something like that, but they had it turned off. So in a pandemic, that shouldn't have happened. And it turns out that 48 hours after this, approximately, my daughter came down with a cold, and then we had to couldn't go to class for a few days, etc. So yeah, an example of using logging. And these meters should be pretty much everywhere. So 800 parts per million in general places is considered an indication of good ventilation. Anything sort of above that, and you should probably start adding other controls. In a home, Health Canada recently came out with updated guidance that actually began before the pandemic, and they're recommending 1,000 parts per million in your home. I found that very useful because I don't actually have a mechanical ventilation system at home, and so I keep it with windows. I'm now my own demand controlled ventilation system, opening and closing windows, and noticing how much more ventilation I get when the temperature drops, even if I keep the window at the same opening. Well, there's another factor that's important for CO2, and that is it represents the rebreathed fraction of air. How much are you breathing in that's come from other people's lungs? And the quick method is we exhale about 40,000 parts per million. It's usually a little bit less. It's usually around 38,000. Outdoors is approximately 400 parts per million. So for every extra 400 parts per million increase in your reading, you're breathing in another 1% of air. So 800 parts per million, you're breathing, every one breath that you take is equivalent, has been in other people's lungs out of 100 breaths. 1,200 parts per million, the sort of ASHRAE standard, represents 2% rebreathed air. And so that indicates a risk as you go further and further up. That day that my daughter's classroom had it when she caught her cold within 48 hours afterwards with symptoms was 5% rebreathed air. And 5,000 parts per million is the occupational health and safety limit for 8 hours of exposure. And that works out to 12%, and 1 in every 8 breaths is basically like you're breathing in everyone else's air. There was one quick question about the spec for the CO2 meter. It is an Aranet 4. And there's a few different places you can get it. In Ontario, you can, well, actually anywhere in Canada, you can definitely order it from Prescient, spelled Prescient, and then an X on the end.com. That's they're located here in Ontario, but there's other retailers as well. And generally, yes, the meter, when you do a calibration for the meter, it will either calibrate to, it's calibrated to outdoor air. So you put it outside and it zeroes it to say 400, or in the case of the Aranet, it's now zeroing it to 420 parts per million. So, but what you really care about is the difference between outdoor and indoor. So that's why I really wanted to make sure when I send the meter off with my daughter in the morning that I make sure she's outside long enough to capture that that outdoor background, because it's all about the difference between outdoor and indoor, not the absolute value. So improving ventilation. Well, we know about using heat recovery ventilators and things like that from the sort of passive house side, but I thought I'd just give a quick example of sort of a small commercial building. There's rooftop units are everywhere, and they provide heating, cooling, and ventilation. It could be a daycare, paint store, optometrist, framing store, bookstore. It's the long tail of buildings, and they're all over the place. And these particular buildings are actually, none of them have the guidance on what to do properly. So I've been actually educating store owners as I go in and have a discussion with them about this. So the simplest example might be an exhaust-only type of building, if you're lucky to have the exhaust. And essentially, what you need to do is make sure the exhaust fan is actually functioning, and you'd be surprised. On some old schools, it's often not. It's been turned off because it's too noisy, because the bearings are shot or something like that. And then you want to make sure the windows are partially open to enable the fresh air to come in from outside. And I've shown it with a split system because so many people still think that ventilation is coming from that nice little box on the wall, but it's not. All it's doing is, of course, just cooling or heating the air. For a rooftop unit, much more common around here, essentially the few things that you want to do is maximize the outdoor air damper position. I can use my little laser pointer. There we go. And the economizer function. So the control that enables this to be open further, and you want to retension the fan belt. If it gets all slippery, all slack, it's basically not going to be providing the same amount of air as it is intended to. And then on the control side, these are usually just simple controls. Just like a house, there's one thermostat, and so you want to make sure that it's actually, instead of being satisfied and turning off as soon as the temperature is satisfied, you actually want to make sure that it's on all the time instead of auto. That does come with an energy penalty, but you won't get the fresh air unless it's actually running. Filtration. So that's the next part. Is filtration is we can actually provide equivalent to outdoor air by capturing the particles that contain the virus. And this shows the mechanism, the main mechanism. It's not sieving. It's not particles having to be captured by like going through a sieve. It's using different, at that level and that size, it's using different mechanisms of diffusion and interception. And it does not remove CO2, so it doesn't account. So if you walk into a place that has high CO2, but they also have lots of good filtration, then that's okay, at least from a risk perspective of COVID or other respiratory illnesses. So what size range are we talking about? The actual virus is approximately 0.12 microns, and the thing is, it's not naked and floating around in the air. It's always contained within a mixture of sort of fluid and salt, otherwise known as bioaerosols or just aerosols. And those size ranges are from about 0.5 microns and up. This is a log scale, so when you look at this on on the actual chart, it's a fairly steep rise in size for filtration effectiveness. So between these two mechanisms of filtration, it sort of adds up to this general curve. And this is a curve that's approximately for a MREF13 filter, I think. So we can actually capture pretty much near 100% of all the particles containing the virus just with a regular decent quality filter, and then we miss a few of them depending on the size. But for the most part, it's pretty much thought to be 80% of the aerosol size is under 5 microns, and much of it, sort of by size, is probably around 1 micron and above. So we're capturing a lot of it. There is still potential for some, all the way down to the size of the virus itself. When we talk about HEPA filters, they're far more effective at capturing particles of all sizes. So, and they're rated essentially at a design point, usually of 0.3 microns, or a most penetrating particle size, which might be around 0.2, anywhere in that range. That's a very narrow range. And then basically all other sizes above and below that, it's effectively 100% or close to 100%. So one of the things I keep seeing on filter, like portable HEPA filters, is they say, oh, it captures the virus down to 0.3 microns and or something like that. But no, it doesn't just drop off. It drops down a tiny little bit and then back up. So it's not that it becomes ineffective. It's actually very, very effective at all sizes. But then likewise for all of the different furnace rating type filters or air filters in mechanical systems, they're all reported based on MREF, which is minimum efficiency reporting values. And this chart is showing the general effectiveness of each filter at different sizes. And typically in most systems, they're running on a MREF8. So it'll be running in this, following this magenta line. So it's still capturing all particle sizes, but it might take multiple passes to get rid of them. MREF13 is kind of the upper limit for many systems, what many systems can handle before a pressure drop occurs. And it's sort of the minimum level that ASHRAE has said you should try to put into your systems for the pandemic, with MREF14 being preferred. It can get quite high efficiency, even down at the sort of 0.5 micron where we're saying is sort of the lower limit of where most of these respiratory aerosols are. So how to include that into your exhaust-only building? Well, you stick in a portable HEPA filter, and or you could make a fan and filter combination using a box fan and 4 filters. That will also filter the air just as well. It just might take multiple passes, but you can move more air through a box fan with the filters and actually achieve overall higher effective air cleaning rates with a do-it-yourself air cleaner. And those are called Corsi-Rosenthal boxes after Dr. Richard Corsi and Joe Rosenthal, who on the former conceived of the idea, and Jim Rosenthal built sort of the first ones. And then for our rooftop unit, we want to upgrade the main filter to a higher MREF rated filter and ensure there's no bypass, or actually reduce the bypass as much as possible, because a bypass is just like having a gap on your mask. It's just going to let air through without filtering it. The last engineering control is ultraviolet germicidal irradiation, otherwise known as UVC, because of the sort of band it's in. It's essentially based that 265 nanometers is the optimum frequency or the optimum spectrum to damage DNA and RNA that's in the air or on surfaces. And it just so happens that low pressure mercury lamps have a spectral output right at 254 nanometers, just a little bit below that. And it's actually fairly safe. It's been used, the picture showing here is from 70 years ago when they were installed in classrooms and used to prevent it was mostly measles, I believe, and tuberculosis. Well proven, they can be very safe, and it's far less penetrating than UVB rays, which actually do cause skin cancer. We still want to design this properly from an engineering perspective to take into account safety and exposure limits, but highly effective, can create the equivalent air changes of like 20, 30, 40, 100 times, which is really not even possible with ventilation systems. And there are some 222 nanometer is kind of coming out. It's not as efficient, it's very, very safe for people, but it's not also quite as powerful, actually killing or disrupting the DNA and RNA of pathogens. You need to have a minimum 8-foot ceiling. Well, you can kind of get away with 7, but minimum 8-foot ceiling recommended, and or higher. And it's you can have it in a pendant style, you can have it fan assisted, but most of them are on the wall, and they're near the top. And there's little louvers that allow the light to come out, and you angle them up and can change them depending on the coverage. So in older classrooms that have high ceilings and no effectively or just natural ventilation, this is a perfect opportunity, and is actually can be installed by someone who has just like an electrical contractor, although it should still be overseen by an engineer or other professional. So putting it all together, we essentially want to do all the things. We want to layer all those controls together. And so what that kind of looks like as a general concept is even on do them all as much as you can, as reasonably possible. Windows partially open, exhaust fans functioning, the system's running continuously, providing fresh air. You can supplement with portable filtration. It still adds, no matter what. Even if you have a hospital room with filter air changes per hour, you can still supplement with additional filtration, because it will intercept it before it actually hits the entire air handling system, for example. Is it worth it? Well, probably not. It's a small amount, but every little bit does add up. Monitoring is very useful with making sure that you are looking at the CO2 levels for ventilation effectiveness. You can use particulate matter counts to determine if your HEPA units or other filtration are actually working properly. If they start dropping, then, or sorry, if you start getting higher and higher particulate levels, you know there's something wrong with the filter or other filtration. Adding UVGI, upper room, which hasn't been done and probably should be a lot more. Maximizing outdoor air damper position and economizer function. Back to the upgrading the filters. You can put UVGI in the actual air handling systems, but then it's limited in its effectiveness to how much actual air is passing through, as opposed to having it in the room where the natural changeover of air moving in the room creates this high disinfectant rate. Finally, you really need regular inspection, maintenance, and filter changes. So many of the systems I've seen in the real world are lacking in that part. So I have extra slides to show a few other things if you're interested. Essentially, I guess in summary, these are all the different ways that you can improve indoor air quality with less cost than plexiglass, which really isn't an engineering control for a predominantly airborne virus. And hopefully this is all much more useful than plexiglass. So.
David, I think you should feel free to share other slides if you want to throw them in.
Yeah. So yeah, I didn't know so many different things are in my head, right, about what I could do. So one of the things that surprised me was this idea of, so getting back to the MREF13 filters, the general recommendation is many systems can't take a MREF13 filter because it's more restrictive to the airflow, and which makes sense. Makes total sense, actually. But I saw that the pressure drop of different products is significantly different between products even within the same manufacturer. And it turns out that the 3M 1-inch filters, the filter with the lowest pressure drop is their MREF13 filter, and that's the one on the bottom here. So it's kind of lost in the low flow range, but in the high flow range, if you compare the same flow rate, it has the lowest pressure drop, which means it allows more air through, essentially. So the MREF11 filter, otherwise known as the Filtret 1000, I had been using it, thinking, it's a good trade-off, you know, it's okay. But then when you actually compare it, I actually get more airflow through this in my home system with the MREF13 and get substantially more filtration, and that's shown in the 3 ranges here. So on the 0.3 to 1 micron range, which is capturing those ultra fine small aerosols or other particles, it's still 62% effective. So it's good. And I've basically done nothing but put MREF13 in our filter in our system now. It's also what I build the Corsi Rosenthal boxes out of, is those same MREF13 filters. One of my sort of advocacy things about on Twitter has been the differing ventilation inequities, essentially, between different classrooms, even within the same school. So this is a school in our region, and it has basically 5 different types of ventilation. The good ones are the new portable with good ventilation, and it has the capability to do very, very high, like probably double the normal, double the minimum level of ventilation. The old portable with exhaust only hopefully isn't used very much, but you know, what's the equity in having a child or class, an entire class, get shuffled off into one room or another, depending on what room they are in the school? It can impact their risk exposure. Half of the building has old exhaust only classrooms that rely on open windows to provide some of the makeup air, and there's no filtration for those either. So yeah, it's if you're going to deploy a portable HEPA filter, instead of putting them one in every classroom, which is equality, you should concentrate them and put 3 in the classrooms that have basically no or limited reliable ventilation. And only after that would you add it to the classrooms that already have ventilation. In this case, it would be the rooftop unit has some ventilation in it, hopefully upgraded, although I know in this case it probably wasn't. And the unit ventilators, they might be harder to source a MREF13 filter for them, but they have filtration. So yeah, so that's my point, is ventilation equity, I guess. I haven't seen that actually happen. It's either like Toronto District School Board putting 1 in every single classroom, or it's just whatever the ministry has said in Ontario, or in many other jurisdictions. They're still denying the use of having this, which is not in Ontario, but other provinces, and that's really annoying. For you building science nerds, this is my favorite thing that I kind of put out there. Quarantine really is a building science issue, and so I've kind of categorized good practice quarantine or isolation into 3 different types. The first one is the gold standard, which is Howard Springs in Australia, relocatable cabins. There's plenty of outdoor air, individual heat and cool units, and they've never had any issues with that. There could be some possibility of transfer between units if they all have open windows or something like that, but it's much reduced compared to any other type of accommodation. Or similarly, compartmentalization, which we know from building science is the proper way to do, multi-unit residential buildings to prevent airflows throughout the building. And then so from an energy perspective, it's fantastic. Every unit should have, have its own individual heat recovery ventilator in it, and that helps greatly with the air leakage within the building from stack effect of the thing. So it has so many different uses, but it also means that you don't have to worry about air transfer between units. That's the whole point. You can even test it. And then finally, since so many of them are using hotels, well, what type of hotel is best? And the pictures there show a hotel I stayed at when I was doing an evaluation of an apartment building in Outbreak, and it was actually okay because it had continual exhaust. I mean, it wasn't energy efficient, but it worked. And the key parts were there was no outdoor air provided through the window. It was totally fixed and sealed. That many people don't like that, but it actually helps keep the system working properly. The PTAC unit for heating and cooling, just under the window, did not admit any outdoor air either. It was just just heating and cooling using a heat pump. And it was essentially exhaust driven from the washroom, and I measured that. It was I think it was around, well, it's 24 liters per second, 50 CFM approximately, continuous, and then that flowed in underneath the door. So it was effectively a negative pressure isolation room, essentially. So what's interesting is that more recently there was an outbreak report from, I think it was the Hong Kong one. No, now I'm getting confused. I think it was another one in Australia, and they had everything under control except there was one issue. They had operable windows. And so even though they had the pressure differences right, if windows were open in the right configuration, it could effectively, with wind pressure, create airflow from across the hall, which is how somehow it was transferred from one unit to another across the hall in a quarantine facility. And they thought it was because of the opening doors. I think it was because of open windows and continual movement of air. And I checked the weather records for that location. I don't know where the suites were relative, like on the compass, but it was 25, 30 kilometer an hour steady winds for over a day. So there were very high pressures generated on the building that could easily have overcome the exhaust in that particular situation. I don't know if I have anything else. I could keep pulling stuff out of my Twitter feed or something, but
oh, that was great. Thank you, David. I found that fascinating. There were a few questions. David, a time check for you. Are you able to stay around for 5 or 10 minutes and answer
sure.
a few questions?
Yeah.
So did you
Okay.
want to filter those out, or
sure?
Yeah,
well, I'll just go back a little bit. Let's see here.
and that's more
yes,
on the bottom
one
too.
Just on the note of N95 masks, I did actually put that in. Maybe it was harder to see, but yes, it's well, masking in general, but even better respiratory protection is not just about the measure of last resort. It's also a crucial component of source control. And just as how we don't want to put stinky things in our buildings, we want to control and reduce the amount of respiratory aerosols that are being generated. And it's the studies showing comparisons of HEPA filters with masks, and in combination of the two, they always add up. And you get the greatest reduction in aerosols by having everyone masked. But you add the HEPA filtration and it drops even more. So you can't remove the mask. You can't rely on HEPA filters even placed really close to you to replace masks. You still need the masking. and the more the better, like the better quality. So yeah, everyone should be wearing proper respiratory protection, and surgical masks are not respiratory protection. There's a whole history about the whole droplet versus aerosols, but another question was, can equal protection be achieved with ultraviolet light and HEPA filtration versus increased ventilation to 6 air changes per hour? Yes. So we can get to 6 air changes per hour and above. Actually, you can get, yeah, it's all a calculation. It depends on where your UV is. If it's in the air handler, it'll be limited to the amount of flowing through the air handler. Same with the amount of air flowing through a HEPA unit. But yes, the whole idea, there's actually a calculation from ASHRAE calculator spreadsheet. You can get a Google sheet, which takes into account UV, filtration levels, and ventilation with outdoor air levels. And it all comes to this equivalent outdoor air number. So yeah, try and make the target 6 air changes per hour with any combination of those. And that's been done for designing hospital systems as well. In the standard for hospitals, it's a minimum level of outdoor air changes, and then a total number of equivalent outdoor air or equivalent air changes going usually through a MREF13 filter and above. And yeah, there's the filtration. Yeah, to get those higher levels, you're getting diminished, just like insulation, you're getting diminishing returns as you add more and more and more. You have to keep doubling the ventilation rate to have, or to double the air changes per hour, or to further half the concentration in a room. So filtration definitely helps save energy that way. And then upper room can, ultraviolet can achieve those really, really high levels of disinfection very quickly. Trying to think if there's, is there anything else that I was thinking about these?
We have, are all contaminants filtered out of indoor air, including pollutants like methane?
No.
So
Yeah.
Can I talk about that? Sorry, David. Yeah, that was my question. So what they put in natural gas, according to Natural Defense Canada, is that they benzene and formaldehyde. And formaldehyde and according to the PBS video, the PhD was talking about, there's some kind of bacteria that can absorb the methane. But then they were saying that at the exhaust, they were showing a picture of a high rise and at the exhaust area. But does that mean that there's methane inside the building? And then also, then can we measure formaldehyde? And then they would sell these things on Amazon for like $50. Has anybody measured formaldehyde? That's what I want to know. In buildings.
Yeah, there's those are all other aspects of indoor air quality
but those are the toxins that are carcinogens and also directly related to respiratory illnesses. So this is, it's intrinsically connected to recovery of COVID. No, if not the cause. All right, thanks.
Yeah, it's there's health effects of the particles themselves, like just general like smoke particles of like PM 2.5 and lower. So it makes sense to filter all that out. And then addressing the issues of the other contaminants that are in buildings, and basically only outdoor air can really take care of it. There are other techniques to treat air to remove gas phase components. It's a bit of a different story, and not something that you would really want to try and do in widespread use in regular buildings. Sort of the word of warning that kind of comes out is there's a lot of other additive type of technologies that are creating other reactive species and compounds like hydroxyl radicals and things like that, and ions and things like that, that yes, in a chamber can create, can actually reduce different level, like it can combine to particles and help them deposit on filters better and remove them from the air and potentially even kill them sometimes, but they also can create secondary products of reaction. And that's a whole complicated chemistry that people are only beginning to really kind of measure, especially in a room. So if you are in a classroom where there's all sorts of stuff that's off-gassing from the people and all the things that are in it, and then you're introducing highly reactive species into that, chemicals into that air, you can be creating quite a lot of other issues. So there's a lot out there. The main thing is sort of buyer beware, or just stick with the things that we know have always worked. And that's the whole point of the presentation, which is ventilation, filtration, and ultraviolet germicidal radiation.
All right, thank you.
So kind of related to that is that some activated carbon filters can definitely attract odors and take out other gas phase components as well. Not really CO2 though.
I think I'm going to watch this presentation like 3 times, David, when we put it up on YouTube.
I've got one. I've got a Mathy one for you. How long does it take? How much air cleaning do you think you get with one air change? Do you think that what happens? So if I've got smoke in a room, fixed amount in the air, and I introduce one air change of outdoor air, how much is left or how much is removed?
There's no prize, but make your votes on the chat. How big is the room?
Doesn't matter. What's the percentage?
Right.
Is it 100%?
Oh, we're getting 90. We vote for 90 and vote for 10. Well, the curve is going to be big.
So turns out with mixing, it's just like adding, cream to coffee, or trying to dilute. You're having to dilute the air. Every amount you put in, you have to remove some, and it's always a mix. So it turns out that with one air change in a fully mixed room, you reduce the concentrations of a contaminant by 63%. So 37% still remains. You do another air change, another 37% remains of that. Do another air change, and at that point, you are essentially at the so it's 37% times 3, and you're at the sort of characteristic 3 air changes equals 95% reduction. So that works out to like a fallow time at a dentistry or something like that between patients. They say you have to have 3 air changes. Doesn't matter if it's per hour, you have to wait an hour if you have 3 air changes per hour. So the idea is increase the effective air changes with filtration or with ventilation, and you can reduce the contaminant levels much faster. So it's always about it just takes extra time to dilute that there's always some little bit left until you get, I guess, to homeopathic levels of contaminants.
Well, it's 8:24. Do you have any final thoughts, David?
I think that was the last one.
Well, that was incredible. And there's lots of people sharing my views here. That was very interesting and well put together. We all really, really appreciate it. So thank you so much. Where's my little icon? So cheers for that. This will be up on YouTube in a little bit of time. People that follow our YouTube channel, which you should subscribe to, will get it automatically sent to you. Otherwise, if you have questions, info@passability.ca, and we'll try to help you. Thank you, everybody. Thank you, David. Take care.